So whatever I've just said, that we have this current equation that we have derived, delta Px here, delta Nx here, Jp, which is diffusive, also decreases, and Jn is also diffusion, minority carrier current. It also decreases due to recombination here. And once you do that, and we assume negligible recombination here, negligible recombination, so this is constant here, and then you know the current here, you know the current here, you add them up, you get the total current, and then you can get the Jp here by subtracting it from the total current, and you get the Jn here by subtracting, right? So these that's how Jp and Jn flow. And then we were just talking about the drift and diffusion component here. So we said delta Px varies like this, so delta N also varies in this particular manner here to keep the region neutral, and therefore you get Jn diffusion, which is negative because the electrons are also decreasing in this particular manner. So the direction of diffusion current is negative. So you get diffusion current here, diffusion component here, and then of course the sum of diffusion current and the drift current must be equal to Jn, and so the Jn drift current then goes in this particular manner here. Okay, and as I was saying, if drift current goes in this particular manner, then the electric field will also decrease like this here. There'll be a slightly larger electric field, and then the electric field decreases as we go further into the bulk here. All right, so then we have said that the current, as I mentioned in the last lecture, we say current in a PN junction is minority carrier limited. Okay, and the reason we were saying was that it is this component here, minority carrier current Jp here in N region, and minority carrier current here. These are the controlling currents. Although at any particular point, in fact, if we go back and look at this particular picture, sometimes we say current in a PN junction is diffusion limited or is minority carrier current. But then those are incomplete statements, because if I go and look at a region here, somewhere over here, then we know that diffusion components have all died out. If I go and look at a region here, diffusion components have died out, and all I get is a Jn drift component here. So current then here is drift. And not only that, the current Jn drift is a majority carrier current, right? So the statements that current is minority carrier or majority carrier is not, strictly speaking, not true. I have regions where current is purely majority carrier current. And then as I approach the junction, the current becomes both majority carriers and minority carriers here. And if I look at any particular point, the current has drift components, diffusion components. It's more complicated. But it is minority carrier current in the sense that is the minority components here which really determine what the currents are. Okay, it is this one Jp here, which is a minority carrier current, which you see here. This component is dP by Lp Ni square over Nd. It is this component here, and it is this component here, which are the currents which really determine what the total current is. Okay, once you know this, so for example, if I were to look at the majority carrier current here, the holes here, who determines the majority carrier current here? It is this one here. For example, this minority carrier current here determines how much is the majority carrier current at this particular point. And how this majority carrier current further varies depends on this minority carrier current. So really the components which are determining what the overall currents are the minority carrier components that you see. Okay, so in that sense, we say it is determined by minority carrier components, not that the current is minority carrier. Okay, so that and a very simple test is, if for example, if I say a current is determined by majority carriers, say take an N-type semiconductor, simple N-type semiconductor, you know that it acts like a resistor, and the current is determined by majority carriers, which is electrons. If it is majority carrier determined, if I say, suppose I double the majority carrier concentration, I double the doping, what will happen to current? It will double, right? Now, if this were majority carrier dominated, if I double the doping of p-type, what would happen? Double, but what happens here? Look at the expression. If you double the doping of p-type, double the doping here, it decreases. So if you double the doping of p-type and double the doping of n-type, the current becomes half. So obviously it shows you that it's not majority carrier determined. If it were majority carrier determined, the current should have doubled. I have more carriers here. But because it's minority carrier determined, minority carriers actually decrease. As you increase the doping, minority carriers decrease. And similarly, this component decreases here. So in that sense, you are seeing here that increase in doping results in decrease in current for a fixed applied voltage. That shows you that the current is determined by minority carriers and not by majority carriers. Okay. The other thing is, which is interesting, that when you forward bias a PN junction, the current is made up of, at the junction, made up of some holes and some electrons. So there's a hole component and there's an electron component. These are the holes which have been injected, and these are the electrons that have been injected. The ratio of these two is important. So Jp by Jn, what do we mean by that? Jp by Jn, Jp at this point and Jn at this point. Okay, so these are the two injected current components. If I look at the ratio, Jp by Jn, so which are this term here? This is Jp. All this is Jp term here. Okay, and all this is Jn here. So all I need to do is take this particular part here, multiplied by exponent QV by KT here, and take this particular part here, multiplied by this. These are the two components, and I take the ratio. When I take the ratio, you get dP by dN, ln by LP, Na by Nd, and all that. And for a moment, what I have deliberately, normally in a PN junction, the region here and the region here are the same. Is both of them are silicon, both of them are germanium, both of them are gallium arsenide, is the same. But it can happen that the material here, you can make a PN junction such that the material here is different from material here. That is why I've written here that Ni, for example, in the N region could be different from Ni in the P region here. All of you know that Ni depends on the band gap. So if I have a different semiconductor here, I have a different band gap. If I have a different semiconductor here, I have a different band gap. So to keep the equation general, we have put Ni(N) square by Ni(P) square here, saying that in general, the material here and material here could be different, and then I have to use different Ni's in these two places here. Okay, so the ratio of Jp and Jn is given by this expression here. Why is this important? Well, after we are done with PN junctions, we'll see a bipolar transistor, which is shown here for simplicity. And note that in a bipolar transistor, as you forward bias, you inject holes, and these holes are the ones that go eventually into the collector, and they make the collector current. While the electrons which are injected here, they constitute the base current. And therefore, in order to get a high current gain, you would like to make this current much larger than this particular current. That's what you would like to do. So hole current you would like to make larger than the electron current in a PNP transistor. So this is important. That's why this ratio I'm writing is very important. What is the Jp divided by what is Jn here? So now the issue is you would like to make this ratio large. So how do you make it large? Well, you don't have much control over diffusion constant. Mobilities are material parameters, and you don't have much control. Ln and Lp, these are also, remember, diffusion length is square root d times tau, lifetime. To some extent, you can change these things, lifetime and all that, by adding impurities. But these are not the dominant parameters by which you alter the ratio of Jp by Jn. A much easier parameter through which you can control Jp by Jn is the doping. And you can see why I would like to make doping higher here and lighter here, because Na by Nd. So if you make the doping higher in P here and you make the doping lower in N here, Na by Nd becomes large, and therefore this current component becomes much larger than this current component. Okay, and that's why you know now why you make emitter P plus. You make it P plus because of to get higher hole component rather than the electron component here, and that results in larger gain here. Okay, so this equation tells us why we make a bipolar transistor with emitter as P plus and base as N. It also tells you something interesting, that sometimes it becomes difficult to make doping very, very high. For example, for the emitter, there's a range beyond which you cannot go. If you go to 10 power 19 or 10 power 20, you're reaching the solubility limit of the dopant. And after that, the dopants are not very active. So there's a range beyond which you cannot go, right? And then you have to decrease N if you want to improve the ratio here. Now, you can't decrease the dopant density also too much here, because note that most of the depletion region, as you can see, is here. And the base width that you see here, you would like to make it short for other reasons, for speed and all that. You would like to make the base width short. So now if you make the doping small, then what happens is the two depletion regions that you see here, they start touching. They start touching, and it's almost like you don't have any base. And then the transistor doesn't work properly. So you can't decrease the doping too much also. So there are limits to how how large this particular ratio you can get, Na by Nd. Okay. Then if you still want to increase the current gain, what are you left with? Well, not much. If you take this as silicon and this as silicon, what can you do then? You can't alter the dopings too much, and these things, as I said, are relatively constant. But then that's where this parameter becomes important. That if you make, let's say, you want NIN to be larger than NIP, and how can you do that? Ni depends on the energy gap, right? So what do? You make N, you make the energy gap here smaller, and you make the energy gap here larger. So as you make the energy gap in P plus larger, Ni becomes small. And note that these things are exponentially dependent on band gap. And therefore, if you use two different semiconductors here, you use a wide gap semiconductor here and a small band gap semiconductor here, this ratio you can get very large. And therefore, you can make this current component much larger than this current component. So that's so NIN by NIP is EGP minus EGN by KT here. And this leads to a transistor which we call as heterostructure bipolar transistor. The modern bipolar transistors, in many of the applications that you find, they use different semiconductors here. For example, they may use silicon here as P plus. Silicon has a band gap of 1.12. And they may use a semiconductor which is a mixture of silicon and germanium. Okay, so germanium, is a small band gap material. And if you mix germanium with silicon, the overall semiconductor has a smaller band gap. And therefore, you can get NIN by NIP square, which is significant. And it adds to the ratio here. Okay. All right. One of the common mistakes that, again, to emphasize, as I said, to improve the ratio of JP and JN, I said make the doping P high, make the doping Na high, right? Now, doping high doesn't mean more holes are injected, right? The ratio increases. As you make the doping high, what happens? Does this current increase? No, because remember, what does this current depend on? Ni square over Nd. So this current does not increase actually. So don't mistake by looking at this that if I make the doping high, I will inject more holes. The answer is no. You don't inject more holes by increasing the doping in P, because injected hole density, what does it depend on? Ni square over Nd. It's independent of P doping actually. It's not how many holes are here that determines what the number of holes injected here, because the current is minority carrier current. So it depends on how many holes are here existing already. So if you want to increase this component here, then what you do is you decrease the doping. Okay, that's why we are saying it's minority carrier current. It's not majority carrier. You can't simply increase the doping here and expect that this JP will increase. It will not. Okay, so if you want to decrease this particular component, then you increase the doping here. Okay, and similarly, if you want to increase, then you decrease the doping here. All right, so let's come back. And one of the last, so we have seen that when we derive this particular expression here for current, so a number of assumptions are made, like negligible voltage drop in the bulk, low level injection, minority carrier current is diffusive, and all of that. And we said the first three assumptions basically define an upper limit on the current, how large a current you can have in the device, and still this particular equation remains valid here. This is the one, negligible recombination within depletion region. It defines the lower limit here. As you go to lower current values, you find that recombination within the depletion region becomes more significant, and you can't ignore it here. So let's look at this particular term in a little bit more detail here. Recombination within the depletion region here. Okay. All right. So the what we said was we had obtained an expression for hole current here. We had obtained an expression for electron current here. And we said that we need this whole component here. And we said this is same as this one. But we know now the holes which are going in, some of them will recombine, and then the remaining will come out. So a more general expression is as follows. JP at minus XP. Okay, whole current here. Let's focus on the red component here, the whole current here. JP at minus XP is equal to JP at XN, whatever holes come out, plus a recombination component. So some of the holes that entered, they recombined, and something less came out here. So that's why we've added this particular component here. So now the total current is the sum of this current plus this current here. And so if I add this up here, I get a total current which is Jp minus Xp plus Jn minus Xp, the sum of the two components here, these two. It tells us Jp Xn plus Jn minus Xp plus Gr. So what it says is my total current inside the device, these two we have already found out, is the standard term here. In addition, there is a recombination component. Okay, and this is what we have been neglecting. We are saying that the holes which go here, almost all of them come out here, and we can neglect this recombination component. So the actual current in a PN junction is a little higher than the current that we have calculated. And how much higher is determined by this recombination component. So now our task is to determine what this JR is. How much is to estimate this value here, okay? Now note, JR is what? The holes go in and then they recombine here. So we have to look at recombination within the depletion region here. So recombination we model in silicon. Recombination predominantly takes place through defects and is the Shockley-Halridge recombination, and we have a fairly large expression for recombination here, NP minus Ni square. These are tau n and Et are the parameters of the defect which causes recombination. And what I'm going to do is make some simplification. And the simplification is that it's a defect in the middle of the energy gap. See, Et is measured from intrinsic level. So we assume that the defect level is in the middle of the gap. So Et is 0. And then we assume that these parameters of the defect, lifetime tau n and tau p, are all the same, equal to tau. And then under that assumption, R becomes equal to Pn minus Ni square n plus p plus 2Ni and a single time constant, which is the recombination lifetime. Okay, so with these simplifications, we have how recombination occurs inside. This is true for any region here, how recombination occurs, but we'll look at this particular within the depletion region here. So Pn minus Ni square n plus p plus 2Ni 1 over tau. Okay, so the next thing that we do is the following. The total recombination current would be, this is recombination at any particular point, and if we multiply by Q and we integrate from minus Xp to Xn, it gives us the total recombination current. Okay, this is the recombination current, volume recombination current, and you integrate it over the entire depletion region, you get the total recombination current. And to get the current, you have to multiply by Q. Okay, so we have to do this here. Now we know that within the depletion region, we have already shown you that P multiplied by N is Ni square exponent QV by KT. We had shown you earlier, you assume quasi-Fermi levels to be flat here, you assume quasi-Fermi levels to be flat here, and then the difference between the quasi-Fermi levels is V, and NP is always equal to Ni square exponent difference of the quasi-Fermi levels here. So NP equal to Ni square exponent QV by KT we know. So then our recombination current becomes as follows. Q, because we have Q here, and if you put here Ni square exponent QV by KT, Ni square you can take it out, so that's what here, exponent QV by KT minus 1 goes here. And what you are left with, 1 over P plus N plus 2Ni integrated from minus Xp to Xn dx. So this is the hole density within the depletion region, the electron density within the depletion region, plus 2Ni integrated over here. Okay, so that's how we need to get the recombination current. All right, so now the integral, we know that the hole density is varying very rapidly. I have large hole density here, almost equal to the doping here, and then the hole density rapidly decreases and comes here, and it becomes equal to the value that we know here, injected hole density here. Similarly, electron density is varying rapidly here. Okay, the hole density goes like this here, the electron density goes like this here. Now, if you look at this integral, where will the maximum value of this integral occur? Note that it is 1 over P plus N plus 2Ni here. Where will the maximum occur? If you look at this region here, what happens? Hole density is very high. Electron density is low. But then what will be this value here? Small. If you look at this region here, the electron density is very high. The hole density is small. Again, the value of this particular is very small. If you go somewhere inside, then you have both holes small and electrons also small, and the value is large here. So what we expect is something like this here. If I look at this particular term here, right? If I look at this particular term, and this particular term is what? Is defining recombination. So if I look at recombination, which is N plus P by 2Ni, recombination is going to be small here, and then peak at one particular place here, and then fall again. At the edges, it's going to be small. Here it's going to be small, and there will be a peak here. Where will the peak occur? At the junction where P equal to, is easy to see that recombination peak will occur where P equal to N. Because if P is much larger than N, again is small. If N is much larger than P, again is small. So the peak value occurs where P is equal to N. And now N and P are equal to Ni square exponent QV by KT. And if you put P equal to N, then the peak value of recombination is occurring at N equal to P equal to Ni exponent QV by 2 KT. That's where the peak value is occurring. And one can show that this, the carrier density is falling very rapidly. Because remember, carrier density goes exponentially with voltage, and voltage is changing in this particular region here. So carrier density is varying very rapidly here, very rapidly here. So this recombination peak that I'm showing here is actually very sharp. It's pretty sharp here if one were to calculate this one here. And the peak value is over here. And the peak value is given by when I put P equal to N equal to Ni exponent QV by 2 KT. And note that this 2 Ni I can neglect because P is what? Ni exponent QV by 2 KT. So it's much larger. P and N are much larger than Ni. So you can forget about this particular term. It doesn't contribute much. So our peak value is this. So what I'm doing is the following. Now, I have to do this integral 1 over P plus N plus 2 Ni. And 2 Ni, as I said, I can neglect. So what I'm writing is that this particular integral is equal to 1 over 2 Ni exponent QV by 2 KT. What is this particular term? Where the peak occurs, right? Multiplied by W effective. I have to do this integral, the whole integral, right? And what I'm saying is whatever this integral is, I can approximate it by a constant value multiplied by some effective. There's nothing wrong here. It's just the area under the curve. Whatever is the area under R, I can approximate it by a rectangle. Rectangle is 2 Ni exponent QV by 2 KT multiplied by some effective width. So mathematically, I'm allowed to do that. All that I'm saying is that this one can be written as a value like this multiplied by some effective width. Okay, W effective here. What this W effective is, I have to compute such that the area under this blue one is the same as area under the red one. The area under the curves are the same. Okay, anyway. So W effective, then what I do is I know this integral JR, and then I take this integral, I write it as 2 Ni exponent QV by 2 KT. I plug it here, and then I get an expression for recombination current, which is Q Ni by 2 tau, sum W effective multiplied by exponent QV by 2 KT. Now, I have brushed aside the difficult part into W effective, right? So because the integral is difficult to do it analytically, it's just time consuming. It's not that conceptually difficult, but I've brushed everything in, the fact that R is changing, I've brushed it aside and put it into a W effective here. But I've got an expression for current. The expression for current says recombination current obviously depends on recombination lifetime, 1 over tau. And very interestingly, it goes as exponent QV by 2 KT. Right? It doesn't go as exponent QV by KT. And, one can show that this W effective is approximately equal to pi by 2 KT by Q, and F naught is the value of the field at this particular point here. Whatever is the field at this particular point, you put that here. I'm not going to derive it for you. Some of the textbooks have it, and for those of you who are interested, I can pass on some notes. You can take a look at it. So W effective is pi by 2 KT by Q F naught here. So that brings us then the following, that the total current in a PN junction is the components that we calculated earlier plus a recombination component, which is Qni by 2 tau, pi by 2 KT, QF naught exponent QV by 2 KT. All right. Now, if you compare these two components, one of them is increasing as QV by KT. The other one of them is increasing as QV by 2 KT. So which one is increasing strongly with voltage? Obviously this one. This one increases slowly with voltage, relatively slowly as compared with this one here. Okay, let's compare the two components. So remember, we were looking at this particular example. We have is a PN junction like this with doping of 5 times 16 on both sides. Diffusion constants are here, lifetimes are here. And with these values, I can compute both the components here. So let me do that. The first component that you see here has a value 1.75 into 10 power minus 11 exponent QV by KT minus 1. The second one, all this is 1.3 into 10 power minus 8 exponent QV by 2 KT. This is 10 power minus 8 and this is 10 power minus 11, 1,000 times stronger than this particular one. But this is QV by KT, this is QV by 2 KT here. So what would you expect now? Can I neglect this recombination component? If yes, under what condition? Where do you think the recombination current would be important, where it will not be important? This equation will tell you. Huh? High voltages, what would happen? Because this is QV by 2 KT and this is QV by KT. So note that if I take voltage equal to 0 or very small, then this current is 1,000 times smaller than this. But then as I increase the voltage, this is increasing rapidly. This is not as increasing as rapidly, right? So eventually what would happen is both of them will become equal. And then this term will begin to dominate. Okay, so let me show you now, put in some value here. If I apply 0.6 volt to my device, the first component is 0.185. The second one is 0.0013. 0.0013. So obviously now it's significantly smaller than this one. I can forget about recombination component. And I can say, well, my current is simply Q dp ni square exponent QV by KT. So when I'm 0.6 volt, 0.65 volt, reasonably high currents, I can forget about the recombination component. But suppose I do the same thing not at 0.6, I do it at 0.3. At 0.3, the first term turns out to be 1.8 microamperes. The second one is 2.57 microamperes. Both are the same, almost the same at 0.3. Obviously, I cannot neglect recombination component now. So as I go to lower currents or lower voltages, I can't neglect. And if I were to do it at, let's say, 0.1 volt, then obviously you would find this component becomes much stronger here. Okay, so that's the behavior of a typical PN junction diode here. Okay, and let me show you a graph. This is how it looks like. A typical PN junction, if you go and measure, you will find, note, there are several regions here. There's a region like this here, where the current is predominantly, that you see here, is normal exponent QV by KT, right? The current is QV by KT. But then as you go to lower, what happens is there's an additional current, which is the recombination current here, right? So this is where recombination current component comes in, and it goes as e to the power QV by 2 KT. As you go to higher values, what happens? The voltage drops in N and P regions start coming into picture here. And so the current no longer increases exponentially. It starts to level off. Okay, so three distinct regions are there. This is the high current regime where the current is no longer purely exponential here. This is the place where your ideal diode equation is valid here. And then you go to lower, you start getting recombination currents here. Okay, and so we have this concept of what we call as ideality factor. Right? So in general, whenever you see an exponential current, you say J equal to Js exponent QV by NKT. And N is what we call as the ideality factor. The reason being is, for my ideal diode equation, we know that N is equal to 1. Okay, and so N is called the ideality factor. And from this equation, one can, especially if N were changing with bias, one can define N as 1 over N equal to KT by Q dL and J by dV. Okay, so I take L and J, and I take derivative with respect to V and multiply by KT by Q, I get an ideality factor. So now we have a total current in a PN junction, which is this term plus a recombination term, which means what? That we have two components in a PN junction. One component which goes as QV by KT, and the second component which goes as QV by 2 KT. So what will be the ideality factor for my PN junction? What will be N? This is the actual current, one KT component and another 2 KT component. But if I think of it in terms of a single exponential with an ideality factor N, then what do I expect? At higher biases, N will be equal to 1, and at lower biases, N will go towards 2. And this is what I was, and you can take this equation and take its derivative, and you can show what is 1 over N equal to. You can write this out. And this is what I was trying to show you. That if I look at this particular region here, my equation can be fitted with an ideality factor close to 2, close to 1. If I look at this particular region here, the ideality factor is 1.69, which means what? Both KT and 2 KT components are present here. If I were to go to even lower, then I would get primarily 2 kT. So ideality factor starts off with a value equal to 2 at very low bias, move towards 1.8, 7, 6, 5, and then eventually reach a value equal to pure ideality factor equal to 1. Right? So there is a region here where ideality factor is 1, pure ideal diode equation is valid. But then as you go to higher biases again, it departs from this value here. Okay. So this is the behavior of a normal PN junction diode here. Both current components are present here. Exponent QV by KT and exponent QV by 2 KT. And especially at lower biases, this is something that you cannot neglect. Okay. And at higher biases, of course, this one is there. Now, so we've seen now the recombination component here. So for the time being, let's focus on this part here. This part here, okay? So if I look at the current increases, it's almost like an ideal diode equation. But then as I go to higher and higher biases, you start seeing this curving here. And therefore, a PN junction has a maximum current limit. You know, for example, I would not like to operate my PN junction here. Why? Because normally, you know, in various applications, PN junction in the forward bias means what? Ideally, you would like the drop across it to be very small, right? But here, what happens is, when you go here, the drop across the PN junction is becoming larger. In fact, you know, if I go even higher, it may become 1 volt. So if you have 1 ampere current going in, and you have 1 volt drop across a PN junction, so you can imagine 1 ampere into 1 volt, how much power is dissipated then. You don't want that to be happening in a PN junction. So there is a, you know, when the current significantly begins to depart from exponential, you don't want to use a PN junction beyond that particular value, okay, because the drops are becoming very large. So there is an upper limit on current, how large a current you can have, which is flowing in a PN junction. How do I determine this upper current? Well, let me show you something interesting here. The same current I've plotted, red one here. And along with that, this green one, it shows you excess hole density divided by ND. Divided by ND, right? So if you go and look at it, this is the excess hole density here, divided by ND. Now look at, if I say my maximum current is somewhere here, right? It has significantly departed from exponential, this point here. And I go and look at what is the excess hole density here. What do I find? Excess hole density is almost become comparable to the background doping. It's starting to becoming comparable to background doping. Which means what? Remember, one of the assumption was low level injection. That injected carrier density is much smaller than the background doping. So as long as delta P is much smaller than ND, you have a well-defined exponential region. But if delta P starts becoming comparable to ND, it starts departing from exponential and starts to saturate. Okay. So if you want to know what is the highest current density that I can get in my PN junction, well, there is a bit of subjectivity, but what we can say is the following. The highest current density that I can get in a PN junction, let's take a P plus N junction here. So when I take P plus N, I can forget about the NA part here. I can only keep the first part here, right? So P plus N junction. So Q dP LP Ni square over ND is the equation for current here. Up to what is the highest current density that I can get in this PN junction? Well, the highest current density is when the injected carrier density becomes comparable to the doping. Okay, so what I do is Ni square over Nd exponent QV by KT, I make it approximately equal to Nd. Because it's under this condition, when the injected carrier density is becoming comparable, that I have significant leveling of my current here. So highest current density that I can get then is you take this here and put it equal to Nd. Approximately. So that's the maximum current density that you can get in your PN junction here. A P plus N junction here, when the injected carrier density becomes equal to Nd here. So approximately Q dP LP by into Nd. What is the maximum current that you can get? Well, current density multiplied by area. Right? Now, one of the interests is in making diodes with a very large current handling capability. How can you do that? You want a diode which can handle currents of 10 ampere. Or somebody wants a diode which can handle current of 100 amperes. How can you do that? Current handling capability of a diode, how do you increase? What are the parameters that you see? DP and LP is not something that you can change a lot. So under your controls are increase doping or increase area, right? Which one would you prefer? Which one will you prefer? Area? Increase area is very simple, right? Increase area, you get more current. Very simple. What is the drawback? Well, the increased area, this picture tells you, the cost is determined by what? The cost of processing a wafer. The cost doesn't depend on each individual diode, right? You process the whole wafer at a time. So you have a cost of a wafer. If you increase the area, how many diodes will you get from one wafer? Less, and the cost goes up. So that's the price that you pay. If you want a diode with a high current handling capability, you'll have to make the area large and it becomes costly. Well, if you don't want to do that, then what do you have to do? Make ND large, and what will happen? Increase the doping. What will happen? Increase the doping. That's the next thing that we'll do. We'll look at reverse characteristics. The breakdown voltage decreases. Okay, so if you make the doping high, the breakdown voltage becomes less here. So now that's the price that you have to pay. So now think of a diode, very high current and very high breakdown voltage, right? How can you get that? Very high current and very high breakdown voltage. Very high breakdown voltage means ND very small. Very high current. How can you get very high current? Area very large. And therefore, the most expensive diodes will be what? You go and look at in the market, and you maybe go and check. The most expensive diodes will be highest voltage, highest current. Right? Those are the most. If you have 1000 volt diodes, 100 ampere current, that's going to be really expensive diode. Okay, so this is all coming from these simple equations here. Okay, so let's stop here then.